Hello everyone, welcome to Canal Physics. In this video we will learn about scalars and vectors.
Before we start today's video, don't forget to buy your copy of Physics Foundations. Please click the link in the description below. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Now let's start today's topic.
Scalars are quantities that do not require a direction to be fully defined, whereas vectors are quantities that do need a direction to be fully defined. Below I have a table of examples of scalars and vectors, and we will learn more about these quantities in future videos. Here you can see that speed is a scalar and velocity is a vector, so these two quantities are commonly used interchangeably in everyday language. But since velocity is a vector, it technically needs a direction as well as the value in meters per second or kilometers per hour to be fully defined, whereas speed being a scalar does not need the direction. For example, if I have an object that moves 6 meters per second to the right, I would quote the speed like. However, the velocity must be quoted as such. Another example is distance being a scalar and displacement being a vector. So let's say an object has moved 10 meters to the west. Then I would quote the distance and displacement as such. Let's do one more example for good measure. Let's say the mass of something is equal to 1.5 kilograms. Then I can quote the mass as, so because mass is a scalar, a direction is not required. And even just saying it with a direction sounds weird. 1.5 kilograms north just doesn't sound right. And this is because mass is a scalar quantity. It does not need a direction. But it certainly does need a magnitude. In this case, 1.5 is the magnitude or the amount of mass, and the units, kilograms. I'll finish with force as a vector example. We are going to learn a lot more about forces in future videos, but I'm just going to show you how to quote them properly. And for this video, it's good enough to just know that a force is a push or a pull, and it is measured in newtons, or capital N. And because it is a vector, it needs a direction to be fully defined. So let's say I push something with a force of 3 newtons in a southeasterly direction. Then I would quote the force as. So we can see we have the magnitude, 3, the units, newtons, and the direction, southeast. Vectors are drawn using arrows, where the length of the arrow indicates the magnitude. So down here I'm showing you a 20 Newton vector to the right and a 10 Newton vector to the right. So if the 10 Newton vector is 1 centimeter long, then the 20 Newton vector must be 2 centimeters long. Also, the magnitude of a vector can be positive or negative. And what I've got here in the bottom right is the common convention used. North and up and east and right are considered positive directions, and west and left and down and south are considered negative directions. However, it might be more convenient to switch these positives and negatives around for a particular problem, and this is to try and avoid using negative numbers. And here I have an example vector. As the second dot point suggests, the length of the arrow represents the magnitude. And of course, the direction that this arrow is pointing is the direction of the vector. And we call the pointy side the head of the vector and the other side the tail of the vector. Multiple vectors can be added together to determine the resultant vector. Therefore, the resultant vector is defined as the sum of the vectors. And we use the capital Greek letter sigma to denote the sum. The actual method we use to determine the resultant vector is called the head-to-tail method. And it's really important that while you do this, you don't rotate the vectors, otherwise you're changing the vectors themselves. So this will end up looking like a chain of vectors. And then the resultant is directed from the tail of the first drawn vector to the head of the last drawn vector. As an example here, I have a pink box, and there are 2 hands pushing this box to the right. And you can see these 2 force vectors are 2 newtons and 3 newtons. So let's manipulate these vectors so they become head to tail. So here you can see the head of the 2 Newton vector is linked with the tail of the 3 Newton vector. So as the last dot point suggests, we must draw the resultant from the tail of the first drawn vector, the 2 Newton vector, to the head of the last drawn vector, the 3 Newton vector. And I'm going to draw this with a red arrow. And it's quite obvious that this red resultant force to the right has a magnitude of 2 plus 3 or 5 newtons. So therefore the sum of these forces is equal to 5 newtons. And what's great about the head-to-tail method is that the order in which you add the vectors head to tail doesn't matter. What I mean by this is that I could switch the 3 and the 2 Newton vectors around and I'll still get the same answer. So you can see that the magnitude of the resultant vector will not be affected. So quoting my final answer, the resultant force, or the sum of the forces, is equal to 5 newtons towards the right. So don't forget, force is a vector, so you need to quote the direction as well. And that's it.
Now let's add vectors in 2 dimensions. Here in this example we have the same 2 vectors as before. The 2 Newton vector is still going to the right, but the 3 Newton vector is now going upwards, so they are perpendicular to each other. So this introduces the second dimension, but in this example we now have horizontal and vertical forces, so 2 dimensions. So how do we find the resultant force now? Well, it's not going to be as simple as 2 plus 3 like before, because these aren't in the same direction. Well, even though this problem looks different, we still use the same method, the head-to-tail method. So below here, I'm going to shift these vectors so that the head of the 2 Newton vector joins with the tail of the 3 Newton vector. And I've added a right angle here just to show you that they are at 90 degrees to each other. And just like in the previous example, the resultant vector is always drawn from the tail of the first drawn vector to the head of the last drawn vector. And I'm going to draw this again with a red arrow. And because forces need a direction because they are vectors, I'm going to put an angle here, theta, to define that direction. And make sure you draw the angle subtended between the tail of the resultant vector. So this angle here, it's not the other side here. The great thing with physics is that you can do a problem in multiple ways and still end up with the same answer. For this example, I could have done this the other way around. I could have joined the head of the 3 Newton vector with the tail of the 2 Newton vector, and I'll get the exact same resultant force. I'll draw this alternative vector diagram over here, like so. But just be careful that the theta from before is now here outside of the triangle, because that's the angle to the horizontal. So I'm going to use a different symbol in the triangle to denote this angle. I've used the lowercase Greek letter phi. While we're at this step, I just want to highlight that these 2 diagrams, when vectors are drawn head to tail with the resultant, this is called a vector diagram. Now we're going to determine the magnitude and direction of this resultant force. From trigonometry, it's clear that the length or the magnitude of this resultant force is the hypotenuse of the triangle, 3.60 etc. newtons. Now we'll determine the direction this force is heading in. So we'll solve for theta and phi. Theta is going to be the inverse of the tan of 3 over 2, opposite over adjacent, and phi will be the inverse of tan of 2 on 3. And looking at the vector diagram I've drawn on the right here, phi could also have been determined by subtracting theta from 90, since phi and theta make a right angle. So I'll just write that alternative way in the brackets here. Now we have 2 ways to express the final answer. We could state the direction of the resultant force as an angle to the horizontal, or theta, or we could state it as an angle to the vertical, or phi. Now, test or exam questions will be more specific as to how they want you to express the final answer, but I'll show you both ways today. So stating the direction in terms of an angle to the horizontal, I understand this final answer looks quite daunting, but if you break it down, it's quite logical and simple. So the resultant force is 3.6 newtons at 56.3 degrees above the horizontal, and in brackets I've got rightwards. So I've rounded to 1 decimal place as the question prompts me to. The 3.6 newtons, that's the easy part, that's just the magnitude we solved from the hypotenuse. The reason why we must be this specific for the direction, so 56.3 degrees above the horizontal rightwards, is because there are 4 options for the same theta angle, 56.3 degrees. It could be below the horizontal, or it could be to the left. So what I'm going to do is I'm going to show you all 4 possibilities here for the same theta of 56.3 degrees. And then you'll see why we need to be this specific about the direction. You can see all these 4 vectors here have the same theta angle to the horizontal, but they're all in 4 different directions. So you need to be specific whether the vector is directed above or below the horizontal, and also right or left. And for this particular problem, the direction is above and right with respect to the horizontal. As an alternative answer, let's specify the direction of this resultant force as an angle to the vertical. We can see that the wording of the direction is a bit different if you're specifying an angle to the vertical. So we have to specify whether it's rightwards or leftwards of the vertical, and upwards or downwards. And I'll highlight this on the same diagram I've drawn in the top left, but I'll have to relabel the angles and the above and left, below, right, etc. So I've relabeled the angles here. This time I've got phi. This is the angle to the vertical.
And again, you can see there are 4 possibilities in terms of the direction. So it's important to state whether the vector is to the right or left of the vertical, and upwards or downwards as well. And of course, from our answer, this is our direction. If this were a test or exam question, it would be worth 4 marks. 1 mark for calculating the magnitude, another mark for calculating the angle, and 2 marks for stating the final answer, as there is quite a bit to it.
Thank you for watching this video. If you found it helpful, please like and share it, and subscribe to my channel for more. Also, click the link in the description below to buy your copy of Physics Foundations. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Thank you.